Welcome to the Explainer. Okay, if you're staring down the barrel of your upcoming manufacturing lab evaluation, you are probably feeling a bit of that pre-practical stress. I completely get it. The roar of the machines, the sparks, the molten metal, it's a lot to process. But don't worry, because today, we're breaking it all down. We are going to do a definitive visual walkthrough of every station you'll face, culminating in a massive, boss-level deep dive into the Foundry. By the end of this explainer, you're going to have the exact mental blueprint you need to walk into that workshop with absolute, total confidence. So, here is our roadmap for today. Number 1, subtractive machining. Number 2, forming and joining. Number 3, additive 3D printing. Number 4, the Foundry practical. And finally, number 5, the final takeaway.
Section 1, subtractive machining, lathes and mills.
All right, when you step up to the conventional lathe, you're dealing with a seriously powerful piece of equipment. You'll be using high-speed steel tools cutting right into a mild steel workpiece. Now, what's really interesting here is the chuck, the part that actually holds your metal. You might get lucky and work with an auto-centering 3-spoke chuck, which makes life super easy, or you might end up with a 4-spoke chuck, and that one requires you to manually center your workpiece before you even think about turning the machine on.
And listen, your lab instructor isn't just looking at your final product. They are watching your safety habits like a hawk. So, absolutely crucial point here. Never hold on to the on and off handle. You turn it and you release it immediately. Keep your hands on the cross slides wheel using 2 hands for a smooth, slow rotation. That practically guarantees a much finer finish. Oh, and here's a massive pro tip for your evaluation. Watch the metal chips flying off your workpiece. If those chips are turning blue or brown, yeah, your speed or your depth of cut is way too high. Back it off immediately before you damage the tool.
Now, before you can actually cut anything, you have to find zero. This is a great example of the leap from traditional to modern manufacturing. On the conventional manual lathe, you are literally using a piece of chalk on the spinning workpiece, looking to see where the circle is incomplete and making physical cross-slide adjustments. It's honestly an art form. But if you're assigned the CNC machine, you're completely in the digital realm. You'll use jog or manual data input modes to find absolute machine zero. That's coordinate 0, 0, 0, and program digital X, Y, and Z offsets so the computer knows exactly where the metal begins.
Section 2, forming and joining metals. So, shifting gears from cutting to bending, you can see the theoretical reality perfectly measured out on the left. A 100 by 80 millimeter flat sheet drawing with 6 millimeter and 14 millimeter bend lines. But then there's the practical reality on the right. You have to translate that perfect drawing to the physical 72-inch bed manual bending machine. You'll literally be pulling and pushing the machine's bar to create precise 90-degree and 45-degree angled seams, relying entirely on your own physical force and maybe a hammer to close those final gaps. Now, if your evaluation assigns you to welding, there is one word you absolutely must understand: flux. Flux is a compound coated right on the outside of your welding rods. When you strike an arc and melt the metal, oxygen in the air desperately wants to ruin your weld through oxidation. But the flux, it burns and creates this incredible protective shield of gas and slag right over the molten metal, preventing that devastating oxidation and ensuring a really strong joint. Let's see how this builds across different welding types. As we just learned, MMA, or manual metal arc, requires that flux coating. But contrast that with MIG welding. MIG doesn't use flux at all. Instead, it pumps a continuous stream of argon or CO2 gas over the weld to protect it. Pretty cool, right? Then we look at autogenous resistant spot welding. This is an entirely different beast. It uses copper electrodes to physically pinch 2 sheets of 0.6 millimeter mild steel together, passes a massive current through them until they hit their plastic point, which is just below melting, turning red hot, and fuses them together without any filler metal or flux whatsoever. Section 3, additive FDM 3D printing. All right, quick mental breather as we pivot to the 3D printing station. Knowing your material parameters here is literally everything. If you load up PLA, you need to set your nozzle to about 195 degrees Celsius. It's sensitive and it needs open air cooling so it doesn't tilt. But if you switch to ABS, you need to crank that heat way up to 230 or even 250 degrees. ABS absolutely requires a closed printing environment with the fan completely off. If you cool ABS too fast, the rapid temperature drop will cause your print to dramatically shrink and crack, and nobody wants that during an evaluation. The whole reason we have all these different filaments is that their distinct properties dictate entirely different use cases out in the real world. We can print rigid, high-temperature polymers for aerospace and automotive components, or we can switch over to a flexible material like TPU to print impact-resistant drone parts, or even fully customized prosthetics. Section 4. Deep Dive. The Foundry Practical.
Okay, everybody, shift gears and really focus in with me right now, because we have arrived at the boss level of your manufacturing lab, the intricate 37-step Foundry Practical. This right here is where evaluations are won and lost. Foundry casting, at its core, is just taking a molded cavity and pouring liquid metal into it. In your lab's case, that's 660 degrees Celsius molten aluminum. But the true magic of the foundry, that relies entirely on your medium, green sand. No, actually, scratch the image of the beach. This isn't regular sand. It's a highly specific engineered mixture of exactly 75% pure silica, 18% clay, and 7% water. This exact ratio gives it the perfect adhesive and porous properties. Want to know the ultimate test before you start? Squeeze it in your bare hand. If the moisture is right, it should clump together perfectly, just like a lotto.
To make this easier, we've organized this massive 37-step procedure into 3 easily digestible phases. Phase 1 is all about packing the bottom molding box. We call this the drag. You start by applying a bit of water to the inner walls so the sand sticks, and then you pack that sand in tightly using your wedge and flat rammers. You literally pound it until it makes a solid sound. Next, take your single-piece pattern and carefully hammer it down until it's buried exactly halfway into the sand. You'll create some small vents in the U shape of the pattern, fill it perfectly level, and then use your lifter tool to precisely clean up the edges. Moving right along to Phase 2, assembling the top box, also known as the cope. Step 1 here is arguably the most critical step to not failing your entire evaluation. You absolutely must spread an even layer of dry, moisture-free parting sand over the entire surface. If you forget this, the 2 halves of your mold will permanently stick together, and you'll be starting over. After placing the cope on top, you insert your runner rod about an inch away from the pattern. This acts as the tunnel your liquid metal will travel down. Pack sand tightly around it, carve out a nice funnel at the top so it's easy to pour into, and finally use a wire to pierce 6 vent holes. Those vents are essentially your exhaust pipes for escaping gases. The final phase. This requires the steadiest hand in the lab. You separate the boxes and gently strike the corners of your pattern, just to loosen it from the sand. Carefully extract it, leaving a perfect negative cavity behind. Using a very careful inward motion with your lifter, you repair any crumbling inner sand edges. Then, you carve a small channel connecting the runner hole directly to the cavity, gently reassemble the cope back on top of the drag, and finally, pour that glowing 660-degree liquid aluminum. Let it cool, break apart the sand, and boom, reveal your casting. But wait, the evaluation isn't over just because the metal cools. You actually have to be able to diagnose your work. When you break open that sand mold, look really closely at your piece. Do you see a misrun? That means your molten metal cooled way too fast and failed to fill the entire cavity. Or maybe you see round, smooth little cavities in the metal called blowholes. Well, that means you did a poor job creating your vent holes in phase 2, and expanding gases got trapped right inside the liquid metal. Being able to explain why a defect happened to your instructor is honestly just as important as the physical work itself. Section 5. Acing your evaluation. So, as you pack up your gear and step into the workshop for real, I want to leave you with a somewhat provocative thought. We've looked at everything today, from the ancient, tactile art of squeezing green sand by hand, all the way to the hyper-modern, micro-precise world of CNC automated G-code. In this modern era of automation, does the true genius of manufacturing actually lie within the capabilities of the machine itself? Or does it still reside entirely in the skilled human hands that establish its perfect zero? Think about that as you make your very first cut. Thank you so much for joining me on this explainer, and hey, good luck in the lab.